Hello everyone, my name is Kun Liu, a PhD student from Peking University. I'm very glad to give this talk at SIMS. Today, my topic is leveraging test logs for building a self-adaptive path planner. This is the joint work between Peking University and the National Institute of Informatics. This work is done during my internship at Iterator project. At this talk, I will talk about these four things. First of all, I will give an introduction of my work about the path planner collision problem. And then I will show the approach of how to build a self-adaptive path planner. Then next, I will show the experiments about our self-adaptive path planner. And finally, I will give the conclusion of the future work of my work. So firstly, the introduction. As we all know that autonomous driving is an active research area, so many work and research has put into this area. But there still are many accident reports, such as this, maybe a collision with Tesla. So we believe that big efforts should be spent on testing and improving these kind of systems. For example, before we released our autonomous driving software, we think that we should test it and find the collision scenario as much as possible and then fix it. And we consider a path planner from our industrial partner. So you can see this picture and the red car, the eagle car, which equipment with our path planner. And it will generate the short-term passes during the autonomous driving. And it will select the best one, the best path. But how does it select the best one? Well, it will use a cost function to give a cost to each path and then rank them. And the cost function will consider the criteria such as safety and comfort. And it will use some weights to do that. As for the testing approach, previous work has proposed a search-based testing approach for the path planner. It is able to find avoidable collisions, which consists of two things: collision scenarios and the corresponding weights that can make the car avoid the collision. So maybe we can take this scenario as an example. In the left picture, there is a red car go up and a parked car in front of him. And then there is a scenario car will go down, the black car. By the search-based testing, we can find many testing results. Here is one of them. We can see that there is two simulations that use the same scenario but different ways. The left one, it will get crash, but the right one take a different path. Then it will avoid the crash. So this is one of the tested results. And from all of the testing results, we can find that different collisions can be solved by different ways. So we want to know that from all of these informations, how can we re-engineering our path planner or improve our path planner? To be more specifically, when should the path planner change weights and which weights should it change at runtime? And this we mean that we do this and also as the testing phases before release the software. So here comes our solutions. Our goal is that re-engineering the path planner with the information obtained from testing. And inspired by the idea of self-adaptation, we propose the self-adaptive path planner. It will use the test logs obtained with search-based testing, and then it will identify dangerous situations and adapt with proper ways at runtime. So, secondly, the approach. Okay, this is the framework of our self-adaptive path planner, following the typical map loop architecture. So we have two systems here. The bottom one is a managed system. This is a slightly revised version of the path planner. And then the managing system. It will collect the runtime information from managed system and then analysis what is the proper ways right now, and then convey the proper ways to the managing system. And we can see that there is two map loop and a shared knowledge base in the managing system. And the reconfiguration loop would decide when and how to change the original weights. And then the reset loop will decide when to change back the original weights. And then we can see the shared knowledge base. It will store all the solutions that found through testing. So, how do we construct this knowledge base? Let's recall from previous example. So, this is two simulations that use the same scenario but different weights. You can see that the left one take a path that crashed, and the right one would take a different ways and it will avoid the crash. And we want to know why do they take different paths. In order to understand that, we take all the information from the original and the modified path planner. Firstly, the cost values. But what is cost values? Let's recall from previous slides that the path planner uses a cost function to give a cost to each possible passes, and it will use some ways to balance between many aspects. So at runtime, we can collect the cost of the selected passes, that is cost values. And then secondly, the weights. So you can see here the cost values are slightly different between these two path planner, and also the weights are different. So we take a further detailed analysis about the path planner decision process, and then we found that it's the different weights that lead to the different cost values and then lead to different passes. So what we need to build our knowledge base is the modified weights that can avoid the crash, and then the original cost values that can characterize the dangerous situation. But do we need all the cost values? Of course not. We just need the section that characterizes the dangerous situation. So how can we select the danger section of the cost values? Let's take this scenario as an example. Here we can have found the point, the 10 point t last. That is the last 10 point to avoid the collision. So you can see that if the car change the weights later than this time point, such as the current position, it will definitely get crash. But if the car changes the weights before this time point or just at this time point, it can avoid the crash. So then we can find the time point as the cost values, and then we take k points before, and then that is what we selected. So from this way, we can build our knowledge base, the three element tube. The first one, CVKB, that is a subset of the original cost values. It will characterize the situation that is most dangerous but still able to avoid collision. The second one is W prime, is the alternative weights that can avoid the collision. And finally, the tau, the threshold of the cost value to decide whether to return the original weights. And about the use of the knowledge base, the simple idea is that at runtime, the car would have a cost value, and then we compare it with each cost value in the knowledge base. Secondly, the reconfiguration loop. This loop is only running when the path planner is using the original weights. As for the procedure, it will first collect the cost values and then analyze that whether current situation is dangerous or not. If the answer is yes, it will get the alternative weights and then transfer it to the path planner. So you can see that the analyzer is the most important element here. Its goal is to identify similar danger situations in terms of cost values. So it has to find whether current situation is dangerous or not, and whether can we find it in the knowledge base. As for the procedure, firstly, we will take each element in the knowledge base from the knowledge base. Then we will calculate the Euclidean distance between current cost values and the knowledge base cost values. This will answer the question when to change the weights. And you can see that maybe we can match the many solutions, and but finally we will get the minimum distance, and with the corresponding weights. So this answers which weights we will take. And then finally, the reset loop. This loop is only running when we are using the alternative weights, and it will decide when to change back to the original weights. As for the procedure, it will first collecting the total cost values, and then analyze whether it is below the threshold tau in the knowledge base. And if the answer is yes, then it will return to the original weights. And thirdly, the experiment. For the evaluation of our self-adaptive path planner, we designed these three benchmarks, and all of them are generated from previous work. Benchmark 1, which have 42 scenarios, and this is the same set that we used to build our knowledge base. So, benchmark 1 was just for sanity check. Then benchmark 2. This is the avoidable clearance that different from benchmark 1. So with this, we want to know that whether our self-adaptive path planner can solve the different on-C avoidable clearance. And then benchmark 3. This is all the safe scenario. With this, we want to know that whether our self-adaptive path planner introduces more danger. And then for the results of benchmark 1, we can see that it can avoid almost all the collisions. Only in 2 cases it can't solve. That is because in this case, we have to change the weights in the very beginning. But at that time, we don't have any cost values, so we cannot analyze this and decide which weights to use. And then for the results of benchmark 2, we can see that many collision scenarios can be solved about 66.5. That is a good result. And finally, the benchmark 3. Almost all the safe scenarios are still safe, only one collision, because it is similar to the danger situation in the knowledge base, although it is a safe scenario. And then finally, the conclusion. So we begin our work from the test logs, and the test log is from the search-based testing for the path planner. So this block is our work. We use the test logs to build the knowledge base, and then use the knowledge base to build our self-adaptive path planner. And finally, we can get a prototype embedded with the found solutions. And from the experiments, we can see that our self-adaptive path planner can solve almost all the things avoidable collisions, and also can solve most of the on-sea avoidable collision. And finally, it will not introduce too many dangers in the safe scenario. So that is a good result. For the future work 1, we can do some variations about the knowledge base. That means we can do different analysis of the cost values, because we know that there are different components in the cost values, such as safety and comfort. And right now, we just treat all of them the same way. But in fact, there must be some components more important. So in the future, we can treat it differently. As for second future work, we can test the self-adaptive path planner itself. That means we can iteratively test the self-adaptive path planner to find more diverse collisions. Then that we keep testing the original path planner. Indeed, since the self-adaptive path planner can solve the collisions that store in the knowledge base, the testing will be driven towards to the different collisions. So, thank you for your listening, and please feel free to contact us if you have any questions. And this is my email and my colleague's email. So that's all. Thank you.